Okay, today is one of three sections, or 3 days I should say, for sections 1 and 2 of chapter 6. Okay, we're going to be talking about vectors in a plane. You'll be able to apply arithmetic of vectors, the HMT rule, okay, magnitudes, vector addition and scalar multiplication, and you're going to find a unit vector and resolve a vector. You're also going to look at using vectors in real-world problems as we go today. So two numbers are all it takes to represent both the magnitude of an object's velocity and its direction of motion. Okay. We simply look at ordered pairs of real numbers in a new way when we're looking at vectors. Please notice I'm not using a parenthesis. I'm using that funky bracket, okay? And we might use it a little differently here, okay? So keep in mind we got the brackets going on instead of parentheses. And in your notation, make sure you pay attention to that. To represent the vector, initial point at the origin and arrow pointing to AB. Now, if I was going to do the HMT is head minus tail. And people are like, what? Well, if the head, A, B, and the tail 0, 0, if you find their difference, the head of the vector first, the tail second, the head of the vector first, the tail second, you'll find the distance between those 2 points, and that is your vector notation as you go. And the head minus tail rule takes points, coordinate points, and translate them into vector values. Those vector values can be applied anywhere around the coordinate plane. Okay. Now, two-dimensional, bless you. As we're going, we've got that two-dimensional vector. A two-dimensional vector, V, is an ordered pair of real numbers denoted by a component form of A and B with those funky little brackets. If we're going to 3 space, it would be ABC. So it's an extension of all the things that we are learning. We just have that third component as we go through. The numbers A and B are the components of the vector V. The standard representation of vector AB is the arrow from the origin to the point AB, just like we saw on the previous page. The magnitude of V, okay, magnitude is the length of the arrow, and the direction of V is the direction in which the arrow is pointing. Y'all did this magnitude and direction stuff in geometry when you had it, okay, in chapter 8, section 4 in geometry. And some of you are like, dude, I don't remember that. So we'll review it. It's all about sine, cosine, tangent, going through that stuff and being able to work with Pythagorean theorem. Because really the magnitude is taking your vector and putting your components A squared plus B squared in them. Okay, so your values of A and B, if you find them, go in. And we're going to be talking about that soon enough. Okay, it is often convenient to represent vectors with arrows that begin at points other than the origin. The important thing to remember is that any 2 arrows with the same length and pointing in the same direction represent the same vector. Okay, so remember, they'll have direction, and if it's a push, it's a force that we're putting on. And as long as I have my terminal point, my head minus tail, if I take -1 and subtract -4, head minus tail rule, okay, and if I get 6 minus 2, head minus tail rule, I'll be able to determine that this is 3, 4 for my vector. Well, if I take this one from 0, 0 and go 3, 4, because I'm able to show with 0, 0, 3 minus 0, 4 minus 0 is the same vector, I am be able to show that these are the same vectors by applying something called the head minus tail rule. All it is subtracting the 2 to find that magnitude going through, that direction for A and B. And A and B, you got to think about them as the dimensions of a vertical and horizontal component. Okay? I mean, they don't really look at it like the right triangle, but that right triangle, meaning that you get the magnitude when you use Pythagorean theorem. Okay? But generally, what it is you'll have your A component, your A components this way, and your B components this way, and the resulting force as you press on an object is in this direction, okay, with the way the components would combine. And I just went over the head minus tail rule. I'll get that up a little higher. so you guys can see. I just take the tail, x2, excuse me, yeah, x1 and y1, and I subtract it from the head, x sub 2, y sub 2. Now, going on, hitting after that head minus tail rule. Since I kind of did one already, okay, it might be just your turn, but I'm just going to start you out. We're going to look at this idea. We're going to apply the HMT rule. Show that the arrow from R to S is equivalent to the arrow from P to Q. So you're going to apply the head minus tail rule twice. Now remember, if you reverse it, the sign will be different, okay? So order matters because you're subtracting. So you've got your first one going through. I got S to R. You know, I'm going to take my S vector minus my R vector. Okay, so go ahead and get that done. Because R was the tail, S is the head, so it's head minus tail. Keep the order. Bless you. And as you're stepping through that, you should come up with 3, 4. Now, to make the comparison, you're just doing the head minus tail rule on vector PQ. So go ahead and do that too. Your result will help you be able to explain, hey, they're the same vector. And vectors, again, can be anywhere on the axis as we do this. Those that have the same AB are the same vector. I should probably pop that in there. Although they have different positions in the plane, these arrows represent the same vector and are equivalent. Okay, so need you to know that. Now, I like thinking about slope, and it's, you know, with the A, it's run over, you know, it's run and rise as we go, but we still got A and B as we're going through as far as the direction it's going to go. Okay, so it's going to tell you. Now, as we're stepping through, just working with HMT, an arrow has initial point 2,3 and a terminal point 7,5. What vector does it represent? Go ahead. Find the vector it represents. You know the HMT. Go ahead and write it down. So we got 7 minus 2, 5 minus 3 as we go through. So we got 5, 2. Are you okay with what I did? I know, it's like, whoa. Okay, yes, sir?
How do you know which one is like the head and which one's the tail?
Okay, the initial is the tail. The terminal is the head. Okay, because I start at the beginning, and then as I head out, I stop, and then the initial is considered the tail. So now in the next one, an arrow's initial point is 3, 5. Okay, that's on my tail, and represents the vector negative 3, 6. So I'm missing the head on this one. Okay, what's the terminal? So I do a setup on this. If I want to look at it, I don't know what the terminal point is. Okay, but I got my terminal minus my tail. Okay, my initial, and I'm able to find my vector. So I've got really 2 values I'm working with. I've got x minus 3 equals negative 3, and I solve. Okay, to find that initial value, and it's going to be 0. I do the same thing with my y minus 5. Y minus 5 has got to equal 6. So I've set that up, and I have 11. But as they set this up, what is the terminal point? They want an actual point. It's not going to be in vector notation. It's going to be a coordinate. So when I do this, my terminal point is 0, 11 as I step through. Okay, now in this next one, there's a change as I'm stepping. If P is the 0.43 and PQ represents the vector 2, -4, find Q. What have I done with Q? Is Q a head or a tail? Remember what it looks like. It should be a head because Q is at the arrow side. Okay? P is at the tail side. So go ahead and find your Q. Go ahead and find the Q. Yeah. Well, if you're thinking about the initial and terminal, and the initial being the tail, and the terminal being the head, my initial is P, an array or vector, and you guys learned when you were in geometry in our sequence that a vector is set up like that with the half arrow. But the initial is P and the terminal is Q, which means the head is Q, the head of the vector, and the tail is P. Okay, so if I do head minus tail, I'm really taking my P and subtracting it from Q. So if I have Q, which is x2 and y2, okay, my subscripts. So I've got x sub 2 minus 4 equals 2. And I've got my y sub 2 minus a -3 equals -4. Okay, so that tells me what I do with my setup. I mean, it's terminology I have to be familiar with, and once I know the terminology, this is pretty nice and slick stuff. So I add 4, and I got x sub 2 is 6, and I subtract 3, and I got y sub 2 is equal to -7. And so my Q is 6, -7, but I should check it. I've got, this is +3, and I subtract it, so it'd be, it would subtract, so it'd be my -7. But let's double check just to make sure, because I've got, if I'm saying this is my Q, that's my 6, this is my 6, -7, and I'm looking at that, I've got Q, 6 minus 4 is 2. I got -7 minus a -3 is -4. So it should work out at the end. I should double check that. Okay. No, but I'm okay. All right. It's like I've never made a mistake before. Okay. So in the last one, you have Q, and Q is the terminal point, which is x sub 2, y sub 2. You have the tail, the initial point. Find P, okay, you know, that you're finding, and we're looking at the actual vector itself. So find that as we go through. And if you're wondering what this test is, this exam is going to be looking like, you're going to do some HMT rules, head minus tail stuff. Okay, basic stuff, very forward, but you got to know the vocabulary, and you got to know what's the initial, what's the terminal, and that the initial is the tail, the terminal is the head as you go through for the vernacular jargon that we're working with. Okay, so as I set this up, I've got that situation. So I've got to solve this because 4 minus x is 2. And I've got x is equal to 2. And I've got this going on here. So my final, for my p, I'm looking at 2, 1 for my coordinates. And pay attention to whether you're looking at a coordinate or you're looking for a vector. Okay, and if it's vector notation, you've got the funky brackets. Okay, if it's just a coordinate, you've got parentheses as we go through. Are we okay with that? Okay. Now, when we're going along here, we're looking at the magnitude or norm of a vector. V is also called the absolute value of V. So it's usually denoted by the absolute value V. In some textbooks, it's a double absolute value, just to show you that you're looking at the norm or the magnitude of it. And really, it's the principal value. It's the positive square root, okay, as you go through. So this is a non-negative real number, okay? So in this next one, I want to make sure that you recognize a couple things. What's this absolute value of V originally look like? I mean, you've seen this a ton of times since 8th grade. What formula is it? No painful remembrance? It kind of looks a little quadratic, you know, as far as, you know, the pain of opposite of this distance formula. Okay, no, I was just going with because it's got a square root, but it's the distance formula. And why in the world is it distance formula? Is because if you take your two coordinates, really what you're doing is you're finding the head minus tail, you're applying that head minus tail rule, and you find the actual components of your vector. And then you're squaring the separate components and finding their sum. Well, gosh, you've done that a few thousand times using Pythagorean theorem. If you are on a axis and you're looking for the length of something and you haven't, that was really well done, wasn't it? Okay, let's try that again by running that back. Awesome. And we have this here. That's my horizontal component, and I got a vertical component. Okay? Well, they're right angles. I mean, you'll see us talk about it this way. Okay? As far as the vector and the two different components of it. But really, they combine to be this black vector. Well, if this is your A and this is your B, doesn't that look like Pythagorean theorem? Well, heck, that's all I'm doing. The absolute value is just talking about taking your A squared plus B squared. That's it. And V is just your hypotenuse. We're just calling it a magnitude, the norm, as we go through this. Okay? So here, I'm asking you to do a couple things. You're going to find the magnitude of the vector, represented by ray PQ, where P is negative 3 and 4, and Q is negative 5, 2. So because you're provided coordinates, you're going to use the distance formula. If you were given the vector component form, you just use the two separates and kind of adjust to the Pythagorean theorem. Okay? Go ahead. You guys got the magnitude. You're on. We're all happy with that? Yes or no? Now, harkening back to the distance formula. Weren't things just simpler then? Okay? All right, so we've got that distance formula set up, but really what we did, when that happens, if in a lack of a better picture, I wish this was actually a picture of this situation, but let's just talk about what the distance formula does. It asks you, the user, to find the value here, okay? Because you're going to find the difference between this x, and that gives you the red. And you're going to find the difference between this y, and that gives you the black, and it puts it down to Pythagorean theorem for you, okay? So that allows you to use your vector component form as you're getting it done. So we have the square root of 8, or 2 to the square root of 2. Okay, and you'll notice that as we step through, both would be acceptable as we use an answer, because most of the time we're doing answers as calculations. You're going to find out in the next one, it's actually easier to use it when we're taking the unit vector and using that one value of the square root of 8 versus reducing it and becoming 2 to the square root of 2. And I'll give you an example of what that looks like. Okay. Vector operations. The algebra of vectors sometimes involves working with vectors and the numbers at the same time. These numbers are referred to as scalars. So I'm just going to multiply the vector by a value. The two most basic algebraic operations involving vectors are vector addition and scalar multiplication. You guys have seen vector addition as resultant. The resultant of the vector, which means you add your x term or your a terms and your b terms, your x components and your y components together. Okay, and that's what they're talking about here, the sum or resultant of the vectors, and you're just adding your x's together and your y's together of that vector. And the scalar, you just multiply your x and y by the same value. That's it. Okay, so as we step through, in the tail to head representation, what's the addition of a vector do? When I'm adding a vector, so I have my vector u, and I add it, okay, to my vector v this way, okay, and hopefully I waited long enough there. If I decided to go this direction with my vectors and apply the vector a different way, I still get to the final destination, okay? This pretty much states that vector addition is commutative, okay? It doesn't matter the order. Well, and you always knew addition was commutative. So when you do this, keep that in mind. It comes through that way. So we have the two ways of looking at the vectors. Parallelogram way, as we go through, the tail to head way, we've got those added through. So those are our two basic vector stuff. But really what it comes down to is, you know, commutative property abounds in this. So going on to our next one, we can do scalar multiplication, okay? When we're talking about scalars multiplying, if I have my initial vector u and I multiply by a value of 2, I'm doubling the size of the vector. In essence, I'm multiplying both the a term and the b term inside the vector component form by 2. That's it. It'll double the length of my vector. If I decide to cut it in half as a scalar, it does half the length of my vector. If I multiply by a negative value, it'll flip the vector around. When you guys did this before, we reflected across the XY line or the X line, depending on what we were doing. It just flipped it across the axis. It does a different direction. Okay, it goes in that negative direction the same amount, so it's a reflection. Performing vector operations, that's all I'm going to ask you to do, is practice adding, multiplying and adding in vectors. Go ahead. It's your turn. Get her done. If you got questions about them, remember, A's add to A's, B's add to B's, or if you want to look at it, X and Y, they're very different terms, but we're talking vectors, so it's an A part of the vector, the B part of the vector. We're doing 3 space, it would be the C part of the vector as well. You okay with our first one? Okay? And it's only making sure that I put those coordinates together. And 3, I'm just going, hey, I'm just going to take 3, and I got vector u. So I've got negative 3 and 9 as we're stepping through. They're pretty straight up, pretty straightforward. In C, it's a combo. So I'm going to take 2, and I'm going to multiply as I set it up so you can see what I'm going to add. So I'm going to go 2 times negative 1, 3. Negative 2, 6. Negative 1 times v is negative 4, negative 7. And then I'm going to have that sum happen when I'm done. So I've got negative 6 and negative 1. Questions regarding anything? Is it okay? Scalar, an addition, are we feeling comfortable with that, with manipulation? Okay, cool. Now, I talked about this vector notation thing, and we're going to get to it on the next page. So this word about vector notation, we're going to hit on again. But really, a vector, when we're talking about it, we have the A term, and we have our B term, okay, as they're talking about it. Okay, and we can represent it as, my AI plus BJ, my vector notation as it's designed to convey an idea of single vector V acting on some object. So it's forces from horizontal and vertical distance and seeing what the resulting is. And the result, when I'm done, is their combination out here. Okay, when I'm finally done, that's the result of them acting on an object separately. Okay. Now, when we're talking about unit vectors, because we've done the unit circle is a circle with radius 1. Well, when I'm talking about unit vectors, I can get them back to being a 1 value. So we find out what multiplier we will multiply our vector by to make it a unit vector, and that multiplier is our magnitude. So going back to how we found that square root of 8, we're going to be dividing our vector by the square root of 8, and then being able to determine, or at least demonstrate, that the result is actually 1 by finding the magnitude of the result. Okay. As we go through this unit vector notation, this is the notation we're running through. These are the same, they're equivalent. And remember, the unit vector u, okay, is equal to 1. If I take my original vector v, dividing it by its magnitude, or multiplying it by its magnitude, the reciprocal of its magnitude, I'll be able to get the unit vector. So let's look at that in this next example. In 4, I'm asking you to find, first of all, v. And we have it in vector notation already. We don't have to worry about the distance formula version. We just go after the fact that we have a squared plus b squared in front of us. So if I go a squared, I got negative 3 squared plus my 2 squared, I'm going to end up with my square root of 13. Okay? If I'm going to do my unit vector notation, okay, and remember, on the previous page when we were talking about that unit vector notation takes vector v and divides by our norm, or a magnitude of the vector v. Okay? Are you okay with what I'm doing so far? I'm taking the vector and dividing it by its magnitude. I'm dividing each component, a and b, by my magnitude. So it becomes, if I'm looking at this, negative 3 square root of 13 and 2 square root of 13. Okay? Now, I have found my unit vector. That's my unit vector. If I'd like, I can represent that as the letter u, because it's a different from v, my original vector, because it's a combination of v and being divided by its magnitude. Now, how can I show or verify the length is 1? You got to keep in mind, I have a horizontal and vertical component. The horizontal and vertical react together as a 90-degree angle. So I need to find magnitude. And I'm going to find the magnitude in my unit vector, which means I'm going to take this magnitude, and I'm going to square negative 3 square root of 13 squared plus 2 the square root of 13 squared. What this is doing, it's verifying the fact that the unit vector I just found is actually the unit vector. The result of this should be 1. Okay, if it's not a unit vector, because remember, a unit vector has a unit of 1 for its magnitude. So when I evaluate this, I'm finding out that I've got 9 over 13, that's square root of that, plus 4 over 13, and that actually is 13 over 13 when I add, and it's 1, so the square root of 1 is just 1. So I've checked out. My unit vector, I found it is this. Okay, questions on clarification on that? Yeah.
So do you just, once you find the regular u, an absolute value, do the same thing as...
It's like doing the same thing again, but remember why we did it. In order to get your unit vector, you got to divide the vector by its magnitude. Okay, so we did that. Now, after we did that, we're clarifying, or I shouldn't say clarifying, we're verifying that our finding of our unit vector is truly the unit vector, because the unit vector should have a magnitude of 1. You won't be asked to do the verification very often. When you use it in a problem, you're going to be using the unit vector in the problem, and it won't be, well, you should verify that. Okay? We're going to be confident that your math was correct, and that in finding the unit vector, you just take the vector value, dividing it by the magnitude. Now, two unit vectors, I, 1, 0, and j, 0, 1, are the standard unit vectors. Any vector v can be written as an expression in terms of the standard unit vector. And this is the idea of this, is that you have two different components of your vector. You have your A component and your B component. A being your X component and B being your Y component. And that any vector, and keep in mind, any vector can be described as your horizontal component and your vertical component as AI plus BJ, and I and J being those different components combined. Okay. Here's the vector VAB is expressed in a linear combination of the vectors I and J, and scalars A and B are the horizontal vertical components respectively of the vector. So all they're saying is that you can take a vector components and express them separately, vertical and horizontal. And we've kind of alluded to that as we've gone through. Our next thing that we're going to be looking at is I want to make sure you recognize your horizontal and vertical components directionally. Okay. The vector v is equal to AI, bj. We've got that. We just went over that. But 6 on the horizontal and vertical components. Well, you know, if I look at solving this vector, do you remember solving the vector? Solving and finding taking a vector, the direction and magnitude, and then finding its coordinates, points. Okay, we're going to be looking at some undo and going back to some geometry stuff with using sine, cosine, and tangent to give us those component form coordinates, okay, as we go. The direction of vector v is the direction angle, the angle theta that v makes with the positive x-axis using trigonometry. We see the horizontal component of v is, remember, the magnitude times the cosine of theta, and the vertical component is the magnitude times the sine of theta. Well, gosh. If I were to, like, I don't know, look at this and go, well, isn't that opposite hypotenuse? And whatever my y value was, I go opposite hypotenuse. Isn't opposite hypotenuse sine? So couldn't I do sine of theta is equal to my opposite over hypotenuse? Right? Well, isn't then v sine of theta equal to y? And if I decided to look at my x, adjacent hypotenuse, well, that's cosine of theta is equal to my x over my hypotenuse v. And remember, that's the absolute value of v. Well, that's absolute value of v is cosine of theta equal x. Well, now we can actually look at that and talk about the direction angle and use the direction angle to help us find our coordinates of our vector. Okay? And it harkens back, I hope, to our geometry days, maybe. Or at least, you know, a good spot for sine, cosine, and tangent. By the way, part of this, as we're going through these, if I'm looking for a direction angle, you guys learned in geometry, if I have that as my B and this is my A, and I'm just using this is a part of it. If I was going to find this theta, wouldn't I go opposite over adjacent? And wouldn't that be B over A? So my tangent of theta would equal B over A. So I could find my actual degree direction by just taking my vector component form, B over A, and doing the inverse tangent of it to find my theta. So if theta would equal the inverse tangent of B over A. So we're going to use these in concert with each other to help us find some answers as we go through. And hopefully this recall is going, oh, yeah, I kind of remember this, vaguely. Okay. Now, I discovered resolving the vector. If v has a direction angle theta, the components of v, remember the actual a and b values, can be computed using the magnitude cosine of theta and the magnitude sine of theta. So it's faster. You don't have to like solve each time, but if you don't remember it, you can just go, well, you know, where would the coordinates be, and that you solve for those sides of the right triangle. But here, you just got to be able to remember that's the magnitude times cosine. Cosine's x, remember? Sine is y. And notice that the magnitude, v, and theta is there. And now plug them in and you're done. Evaluate with your calculator. Go. I'll try to catch up as you guys are going here too. Six cosine of 115. 6 sine of 115. Okay, that's it. It's straight up. I got the information. I read it from my graph. Now, I've got up here, pay attention to which quadrant your angle is in. It's not about us knowing which quadrant is when the angle is provided. It's knowing when we're finding it. This is in quadrant 2. It should be more than 90, less than 180. If it's in quadrant 3, it should be more than 180, but less than 270. If it's in quadrant 4, it should be more than 270, but less than 360. So pay attention to that, because we're going to be working with these, and we're going to find reference angles, and we're going to find the final angle by adding 180 or subtracting it from to be able to get our actual angle value. Okay, because we're using that reference angle idea as we go. But I guess I got to catch up, get these done. Six cosine 115. So I've got negative 2.53 in my first one. I'm just going to check my mode real quick. Yep. Negative 2.53, and everything should be to the third 6. And then in my next one, got my sine of the same thing. I got 5.438. Questions regarding? We doing okay? Now, how do we use this stuff in that next question, finding the direction of an angle? I'm kind of disappointed with the way that direction question's asked, because we're going to be working with direction when we are working with from north, and in this one, we're going at standard position. Okay, so we've got the standard position we're working with a direction, and I want to make sure that that's clear, that we're not coming from north. And I think that's confusing when we talk about direction. So if you're flying a plane, we're going to be going from north, but any other directions we're not. Okay, and I'll make sure that there's a definite, clear statement of which direction we're using. But until then, it's in standard form, and remember, it goes counterclockwise for positive values. And when I first did this, I did it according to that v cosine of theta. I'll be honest, I use tangent all the time on these, because remember, b over a. If I use the inverse tangent of this, it's the same value when I'm done. Okay, and I'm looking here for the direction of my angle. So what's my value? b over a inverse tangent. And if I think about it, this is my triangle, that's 2, that's 3. I just want that angle. So if I do the inverse tangent of 2 over 3, I'm going to be way faster than if I do anything else. Okay, if I can see. Okay, so check those out and see what's going on with this. So you got the inverse tangent, right? And 2 divided by 3 is going to give us a 33.690. I get that grouped. As they asked me here, find the magnitude and direction of the angle. Well, I got the direction, right? Are you all right with that? Magnitude. Okay, now keep that in mind. Absolute value of u is representing that magnitude as we look through this. And I've got 3 squared plus 2 squared, square root of 13. So I've got the two things that I need for that particular vector. Are you okay with what I did with the magnitude? Are you okay with what I did with direction? And that direction's from standard position. Okay? Now because of that, keep in mind, my angle in standard position for the second one should be more than 180, right? I mean, just looking at that, if I go around, my value should be more than 180. My first piece of information I'm going to receive using the tangent, A over B, the inverse tangent, is going to be the reference angle there, okay, as I'm going through this. And so we'll do direction first. So if I do my direction, if I can spell it, I got the inverse tangent of B over A. So I got positive 5/2 as I've looked through this. Now that returns 68 degrees. So 199. But remember, that is just this angle right here. That's what that is. Okay? My angle should push my vector into quadrant 3. So I have to adjust that and go, well, I've got to add 180 to that, plus 68.199. Okay? And I get 240.19, is that 191 or 19? Yeah, 199. So I get 248.199. So that's my direction angle right there. Are any questions about why I did the add 180? You okay with the fact that I'm using that reference angle and I've got to know that it's going to be in quadrant 3 at the end, so I had to make the adjustment.
So you do it like just like you would for like the first one, but you have the 180 too.
Exactly. So that's why I got to pay attention to where I'm going to be residing, what quadrant. Because in this first one, it made most sense because that my reference angle and the quadrant it's in, it made sense that that was the degree. Okay. Now, I still got to do magnitude here. So my absolute value of v is equal to negative 2 squared plus negative 5 squared as we get through there. And this is 4 plus 25, so it's equal to the square root of 29. So those two pieces of information I need to be able to get from that. Any other follow-ups with that? Okay. I know it was long today, and I apologize. I made it shorter for Monday in doing this. I also know that today's homework is very short. It seems like it's, forever, but it goes very fast with what you're being asked to find. Okay? So make sure you're aware of that. Please make sure that as you're going through your reviews, you get that 1, 2, 3, and 8. You've getting those going through. We will have time, hopefully, on Wednesday to answer any questions on the 6, and you'll be able to take that quiz on Thursday, and then we'll have more time on Thursday and maybe even Wednesday to answer questions on the reviews.
Is the format of the reviews going to be like the...
Yes, the final is multiple choice, and it's made from the same program your reviews are from, so the directions will be similar, okay, and the expectations throughout. The difficulty level of the final is equal to the difficulty level of the reviews, okay?